don't know to change these settings. Okay, so yeah, there it goes. That's what it normally does, but this one says cloud for some reason. And I don't know, like I've never seen it say with the cloud. And so I think it's going to go to my OneDrive for either Mount SAC or CPP. I don't know which account this is using right now. I think it looks like my CPP account, but that's okay. All right, yeah, it's recording. Okay. But so yeah, what I was saying is just don't convert them to millions because it's easier to divide when they're left as decimals. Because what we're doing is like probability is all about dividing things by totals. And so here what this example is saying is that 61.5 people were never married, 129.5 million people were married, and so on. And so what proportion of the adult population in the US is married? To answer this question, we just have to use the relative frequency rule that we used in chapter 1. And so here, proportion that the US that is married, what number am I going to have as my numerator? So you guys can type into the chat. Yeah, but which one of these numbers is it going to be? Yeah, the 129.5, right? And so for relative frequency and now probability, when you look at the numerator, it's the number that applies to like the thing that you're talking about, right? So how many people were, what proportion of people were married? I'm going to look at the number of people that were married, and then what number am I going to have on the bottom? Yeah, the total, right? And so the total is going to be this 229.1. And so, yeah, I'm always going to have 229.1. And so here, this is essentially, so we used the relative frequency rule. Which is always the frequency divided by the total. And so here, N is 229.1. Is everybody okay with that? Nobody's saying no. Okay, and then here, what proportion of the adult US population never married? What's the only thing that's going to change about that fraction that I just had? Like, is the top going to change or is the bottom going to change? Yeah, the numerator is going to be what changed. So I'm always going to have the total on the bottom. And so that 229.1 is always going to be my denominator. And so here, now I look at the proportion or the number that never married. So 61.5 over 229.1. And so if we convert these to fractions, or not fractions, they are fractions, to decimals, we get, the first one is 0.057. So here, let me move this over a little bit. Oh, 0.57, not 0.057. And then this one is, oh, I didn't mean to do that. I'm sorry. Okay, there we go. Yeah, 61.5 divided by 229.1 is 0.27. So yeah, do you guys have any questions about this first example? Okay. Does everybody, can I scroll? Are you guys okay with me moving on? All right. So this next question says the data indicates that 56.5% of adults in the US are married. And so that's the answer we found in part A. We wrote 0.57, but we rounded it. And so this was the answer from part A. And then so here it says if we choose one adult at random, what is the probability? And so basically what this question is trying to get across is that probability and proportion is basically the same exact thing. So here, the probability, and so I'm going to use that probability notation that I talked about in the notes. And so here, probability, and so if I use that notation, it's just probability that they're married. And so this would be equal to 0.565. And so all I did was I converted this percentage to a decimal. You can give probabilities as percentages as well. That's totally fine. And so here I'll just put or 56.5%. However, I'm pretty sure, so I totally think probabilities can be given as percentages, but I'm pretty sure Pathways, your online homework, is going to want you to give it as decimals because all of their answer keys to everything have everything in terms of decimals. You could even give probability as a fraction and it still means the same thing. But okay, so any questions so far? All right, so this next question or this next part says it's still about the married and not married to the census. And so it says the probability that a randomly selected adult in the US is married is equal to the relative frequency or the proportion. Oh, okay, so it's just, yeah, here's the probability notation. And so here you can just kind of, the sentence is, I already said this. So it's basically just saying probability is equal to relative frequency. And so now it wants us to find the probability that somebody was widowed. And so again, I'm just gonna use the relative frequency rule. So now I have that the probability is equal to the relative frequency. And so widowed is 14.4 over 229.1. And that gives us 0.0628 or 6.28%. So any questions? Okay, so here it says that a Glee Club has 123 members. And so this is gonna be N. And so N is equal to 123. Out of those 123 people, 83 live on campus and 22 live in sort of on campus, not on campus, and then the remainder commute. And so suppose one of those students is selected at random. Are you more likely to select a student that lives on campus or in the apartments? What do you guys think? And so here, you're more likely to choose somebody who lives on campus because there's more of them. So on campus, because the majority of students live on campus. Okay, and then so part 6 says, what is the proportion of students that live on campus? Can this relative frequency be used to represent the probability that a randomly selected student from the Glee Club lives on campus? And so the answer to that is yes. And so I'm going to find the probability that somebody lives on campus. And again, I'm just going to use that relative frequency rule. And so what number am I going to have on top here? Yeah, that 83. And then on the bottom, I'm going to have this n, so that 123. And so if I convert that to a decimal, I get 0.67 or 67%. Okay, so the next question is, what is a reasonable value for the probability that somebody commutes, right? So this in words is probability that somebody commutes. That's how you would say that in words. But we weren't given, so notice we were not given the number of people that actually commute. And so one thing you could do is you could do like 123 minus 83 plus 22 to find out how many people commute. Or what you can also do is you can find the probability that somebody lives in the apartments, so APT for apartments, and then so this is kind of like what do you guys think the total probability should be when I add up all three of these probabilities, the on campus, the apartment, and the probability that somebody's a commuter? What do you think those should add up to? Yeah, 100%, right? And so what I can do is I can find these I can find these first two, not that high. I can find these first two, and then I can just subtract them from 100% to find that probability. And then I don't have to find how many people actually commute, right? I can just find the probability on its own. And so there's two different ways of doing that. I'm going to do the probability way just because we're doing probability and we're practicing with that. And so here, the probability that somebody lives in the apartments, well, that's equal to 22 over 123. So when I do 22 divided by 123, I'm getting 18%. And so that means that the probability that somebody commutes is equal to 100% minus that 67% plus 18%. What's 67 plus 18? Oh, I'm gonna sneeze. Oh, okay, so yeah, this is 15%. Does this make sense? Is everybody okay with this example? With both of these examples that I just did? And so on this website, it's basically doing for us what this example wanted us to do. So if you look at the example in your notes, I can't share two screens at once, but if you look at the example in your notes, it would have had you toss a pig multiple times. Wait, drop the link. Oh, I see. Okay. Somebody at Mount Sac actually made this. So yeah, everybody go to this link. What you can do is if you press toss the piggy, then it'll just do it once. And so it'll do this, it'll fill up a table 25 times, which if you look at the examples, that's what it would have had us do, is toss it 25 times. And so rather than actually tossing a pig, you can just click this 25 times. And so what we're supposed to be looking at for the example is, which one is it? It's on its back. So if it landed on its back, then we're considering that a success. And so here on its back would be razorback. And so it landed on its back 1, 2, 3, 4 times. So here we found that the probability of it landing on its back was 4 out of 25, right? What this thing does down here, and so what we would have done after that is we would have like graphed our results essentially. But what we're just gonna do is we can just say toss the piggy or toss piggy. And what this is doing is it's doing it 100 times. And so I can change this to 25 and then it's graphing the results for us. And so you can see this time, oh, I still got 4 out of 25. And so here, if I do this 200 times, then I still didn't get any of these leaning jowler ones where it lands like on its sideways ear. But I'm getting 41 out of 200, which is about 20%. 4 out of 25 was 16%, so it's still kind of the same. Let's see what happens if I do it 1,000 times. Here, so for Razorback, 226 out of 1,000, that's around 22%, 22.6%, right? Yeah. And so here, we're getting around the same probability every time, but the more that I toss it, so 480 out of 2,000, I'm getting 24%. And so, yeah, this is the pig thing that we were going to do in class, and we're not going to actually do any of that, but it's kind of leading into the next thing. And the next thing is called the law of large numbers. And so if you go to the page 5 on the pathways notes, the definition is right there. It says the law of large numbers states that as the number of trials increases, the relative frequency approaches the true probability. And so what that means is the more times we toss the pig, so 5,000, the closer our proportions are to being the actual real probability, right? And so what I mean by that is, let's say you're tossing a coin and so everybody type in, what would the probability of me getting heads be if I tossed a coin? Yeah, 50%, right? 12. No, yeah, it would be 50% because there's 2 sides to a coin, right? Heads, tails. And so if I flip it, I only have a 50% chance of it landing on heads. And so but how many, so let's say I threw that coin 1,000 times. Would you expect me to get heads exactly 50% of the time? No, that seems a little unrealistic, but it's going to be pretty close to 50%. And so if I were to flip a coin like an infinite number of times, 50% of the time I would get heads. And so the more times you do this experiment, the closer you get to the true probability. And so here, the bigger the numbers that I put in, so 5,000, if I go to like 10,000, then this is 22.8% again, right? Which is really close. I think, oh, I had the answers up here at some point. There's like an actual answer. I know this is the leaning jowler one. I know it's actually 0.06. And so here, if I do, this is what I'm getting, right? If I do 10,000 rolls, I'm getting 0.06%. If I do a million, is this a million? Yeah, 6 zeros. Then I'm getting 0.06% again, right? And so, yeah, the more times that you repeat that experiment, the closer you get to the real probability. And so here, yeah, if we go back to the notes, so let me stop this. Let me start this. So if we go back to the notes, it says the stats professor tossed the pigs more than 10,000 times and he calculated the long-term relative frequency. And so, yeah, we can assume that the long-term relative frequency is the actual probability that the outcome will occur because it's such a large sample. Okay, so I want to say that that's it. There's just a few things down here that we should all kind of take note of. I want to say I go over these in my notes as well. So all 4 of these things actually are super important. So what we call these outcomes is events, right? So each one of these things would be an event. So this is event 1, event 2, event 3, and so on, right? And So, but you can also have, so these would all be simple events. What we're going to start talking about on Wednesday are things called compound events, where it can't happen here, but let's say it lands on its feet and its back at the same time. That would be a compound event. The probability of that happening would be 0, though, right? Another important thing to note is that each probability is between 0 and 1 if you're converting it to decimals, right? And so you can't have the probability be greater than 100%, which means when you convert that back to a decimal, you can't have it be bigger than 1, right? So you can't say that the probability is equal to 1.2. And then again, and so here, let's write that down. So this would be 0% and 100%. And then the fourth one, what it's saying is the sum of all probabilities is 1. And that's what we were talking about earlier. The sum of all probabilities is 100%. And so if you convert that to decimal, you're getting 1. So do you guys have any questions? So that's it for the lecture portion. So are there any